Oh, by the way, if your CFA did not fit well, you couldn't move to the second step. You would have to kind of try to find out why it didn't work. Like maybe uh, maybe you have some residuals that are correlated. Maybe you have a crossroad. You have to figure out why it didn't work. But assuming your CFA fit well, you can move to the second step. Okay. And by the way, if you are lucky to be able to do your study for well-established scales, like scales that have several studies, using them, that they're doing CFAs and finding good model fit, it's very likely that you'll have no problems, right? But if you either developing a scale, having a scale that's new, it hasn't really been studied that much, you may run into some problems. Or you may get lucky, but like my student, that I participated in his dissertation committee just last week, he got lucky. It was scales that were only one study with the FA, but his model fit great. I was like, wow. you know, I wasn't so optimistic. It worked out for him. Okay, so now let's put the direct effects as hypothesized by the author. So the author hypothesized model is this. The distributed relational behaviors predicts both social capital affects vigor affects performance. Now, we need to do something else too. Because now before, these variables here were all correlating, so they were all exogenous variables, like they were not being explained. Now that they are being explained, these are called endogenous variables. Like LRB is still exogenous because LRB is predicting, like there is nothing predicting LRB. But BSC is being predicted by LRB. Therefore, BSC now has error. It's not the same thing as measurement error. These are measurement errors. What you have here now is prediction error or residual, which is the part of BSC that's not predicted by LRB, right? So we need to add that error. It looks the same as this, it's just conceptually different. So now if I click here, and I should move it out of the way. Use the touch up. Okay, that's better. Okay, so this here is the part, it's a residual isolated variable, it's the part of BSC that's not explained by LRB, okay? And if you have to do this, plus ABLES will not allow you not to have a residual, okay? So,
Professor, how did you do that again?
I just clicked here on this add a unique variable to the existing variable. And then I clicked on the variables that I wanted to have a residual. So I'm doing it so these are what's called endogenous. So exogenous is a variable that is a cause. Like they're causing others, but they're not being caused, right? LRB now is the only exogenous. Endogenous are variables that are being explained. So BSC, vigor, and performance are now endogenous. In the CFA, all of these four were exogenous. Now the indicators are always endogenous because they are being explained by the factor, right? Okay, I'm going to move these out of here.
They really should have picked two words that didn't sound so similar.
Exogenous and endogenous. Yeah. But it's standard. You see the same term in econometrics. If you ever took an econometrics class, it's statistics. They pick weird words.
So when we're adding those in, do we have to name them?
Yes. No latent variables without a name. Okay. Now, you could do plugins, name and observe the variables. But I like to name them with R's to differentiate from E's, just so you remember that these are measurement errors. These are really residuals. They're not the same thing. They are, so these are, while for example, E1 is the part of the indicator that's not being explained by the latent factor. This is the part of BSC that's not being predicted by LRB. So I will double click here, and I will just call R1, R2. I believe if you use the plugin, if you said plugin name and observers, they probably would just do E17, 18, 19, right? They would continue the same. Okay, so we have our model. That's the structure equation model. Okay, notes that now it's not the complete model fit by the authors. There is actually a discrepancy between here. Here, right? So in the model that they fit, right? They never draw the indicators here because of space probably, but they did control for 3 variables that they thought were confounders: age, tenure, and gender. I only simulated age and tenure because I was a little more trouble to simulate gender, and I was like, it's not necessary. But we are not including it at this point, right? We'll include it in the next step. But so age and tenure were control variables. Okay, so.
Add that in.
You need to, but let's do it 2 steps just to.
Okay, yeah.
Let me run here by the way, I'm doing this more for didactical purposes. Like, if you were doing this yourself, the first step is CFA, the second step is SCM with all the control variables, right? So you would put age, tenure, anything else you want to control for, right? I'm slowing down here for you guys, but
Just so I'm tracking, we have the residual endogenous variables on those 3 factors and variables because those are
being predicted by something else.
They're dependents. Okay.
Thank you.
They're dependent variables now.
That's what I was making sure I understood. Thank you.
Okay, so this is our model. We are assuming, obviously, that the residuals are unrelated, right? Like that whatever we have here is random, so there is no relationship between the residual and RB. If we had, that would mean that there's a confounded variable here that we didn't account for. Okay, and the model would fit poorly. Okay. So let's save these. Now, let's just do, I'll go back. Right now, let's stick to, we don't do factor score weights anymore. Let's stick to just standardized estimates and square root for correlations for now. We are just more interested in model fit at this point. So
I'm sorry, you clicked off factor.
I left it as it was, which was just standardized estimates and square root for correlations. I unclicked the factor score weights. It doesn't hurt having it there, but yeah. So let's run this and calculate, save, right? And then calculate estimates. Okay, so it fit.
Mine says 2 variables are unnamed.
Oh, you have 2 variables that are unnamed.
Did you do your R1, 2,
Did you put names on them?
Yeah.
Oh, you maybe you misclicked and you put a name on the arrow rather than the variable.
How are you doing? I'm just watching my phone. Okay, and where did you get those numbers from? It was in the data?
That is what the machine is calculating for us.
0.99 CFI, 0.99 with the squared error of 0.99. This is 0.029, right? Close to zero is better here. So, and it's not significant, which is what we want. And then the confidence intervals of root mean squared error are all below 0.05, which is good.
Where are you seeing it's not significant?
Here, this 0.991.
Okay, because that's the 0.95 threshold one.
Well, no, this is the p. The only fit index that gives you a p-value is the root mean squared error. And so,
we're just subtracting.
It's a p-value, right?
So
you
it's
want it
flipped.
greater than 0.05. Yes.
So it's 0.95.
No, the cutoff for our alpha level.
Oh,
is
never mind. It's
0.5.
way. I'm just
This is like the chi-square.
I haven't had my coffee.
It's a test.
Yes.
Okay.
It's way far from 0.05.
You know, the next step would be to do that, to look at the estimates, but we're not going to look at this now. We're going to complete the model because they did control for two variables, right? So if you go back here to your model specification, let's add those two variables that they controlled for. So I will click on variables here. Again, I did not simulate gender. That's why gender is missing. So we just pull age here and pull tenure. Those are observed variables. Tenure.
How are we going to remember?
I have videos for all of this. I'm literally going through what's in the videos. Actually, you have multiple sources, right? My videos go through everything, and then the book goes through everything as well, right? So, no, you just review it before you do it for your dissertation, and you're in good shape. Actually, you're going to do the exercise, right? Which will also help you.
I forgot the variables.
It's actually not hard to remember. I mean, I use Amos just for you guys. So I use Amos once a year, for 3 days.
What do you do if you were doing a study with?
I use R. And I teach my PhD level class using R.
Yeah.
So that's why, it's not that hard to remember because I do it 3 days a year, and I still mostly remember for the next time. Yeah.
Is there a way to close out the file? So somehow my file got corrupted, and so it won't run?
Oh, the data file or this file?
The data file.
I would say just change what the data file is, download it again in the new file name and pick another file.
No. Where did you get tenure and age from again?
From the data file. If you click on the variable names here,
Variable names there. This
Yeah.
one. Okay.
and you scroll down, you
Yep.
see them.
Oh, yeah.
I just clicked on
And so they are, let's look at what the author did. Right, so the author had them as controls for job performance. So they basically say, okay, if these are confounding variables, in other words, if they have a back door, by adding them there, I'm blocking that back door, right? So now this is incomplete because this representation here is very simplified, not only because the indicators are not here, but also because you should always allow the exogenous variables, like the independent variables, to correlate with each other and correlate with other exogenous variables. So linear relational behaviors is exogenous, so you should have correlations here too. So in our model,
Professor,
mm-hmm.
I have a question, and I don't know if you answered it earlier. It's maybe a stupid question, but when you clean up the data at the beginning, you told the data that age and tenure are observable variables, and the other ones are unobservable?
Well, everything that's in the data set is observed, right? Notice that these latent variables are not in the data set. Like you don't have, look at our data, right? You have the items which are observed, and you have age and tenure that's observed. You don't have LRB, BSC, vigor, performance as variables because they are not observed. You know, so latent variables are not in your data set because you don't have, they are not observed. Okay? We only measure them with the indicators which are observed. Okay? Now, when we created factor scores, then we actually created composites and they appeared in the data set. Because that's what I mean by scoring, right? When you scoring means making an unobserved variable into an observed variable by combining the items. And that's how we got them in the data set. But originally, no latent variable will be in the data set because you cannot see it. You only see the manifestations of it, which are your items, right? Does that make sense? Like, I don't know. Yeah. So, yeah. So that's why latent variables, you can call them anything, right? Like, that comes from theory. You know, you have to have theory that says that these three items are good measures of linear relational behavior. Like this comes from your scale. Same thing with Bates and Potsakov, right? He couldn't observe, he cannot directly observe constructive, destructive, supportive, and what is the fourth one? Destructive and defensive. Latent variables, he can only observe. So those four are not in his data set. What he has is a scale with items that measure those. Okay. Okay. So here we have these because you're controlling for age and tenure. Okay. Now there is one thing more because so these are independent variables, which in SCM we call them exogenous variables, right? LRB is an independent variable too. You have to allow them to correlate because they may correlate, and if they correlate and you don't allow them to correlate, you get poor model fit. So age and tenure are probably going to correlate because the older you are, the more likely you are to be on the job for a while. So add that correlation. It's funny how in Amos, if you draw from up to down to up, you get a different direction of the arrow. So go this way to get the arrow this side, and then this is not going to be pretty, but I need. Actually, I can make this prettier by moving this way out here. No, that's fine. Okay. So because our B is independent, I want these correlations as well. Again, you have to allow independent variables, which we call exogenous variables, to freely correlate, because if you don't, you are saying that they don't correlate, which may cause poor model fit. So, yeah. Okay, that's the model with control variables. Now, if this model doesn't fit well, like we saw that the model without control variables fit well. If the model with control variables does not fit well, possible suspects would be that this residual here is not really random, that the residual is related to age. Like, so this relationship here would be a suspect you know, or it could be with here, like the vigor is related to age. Like right now we are saying in your model that the residual, that the part of vigor that's not explained to VSC is completely random, right? It's unrelated. But let's say if vigor is, if this residual is related to age, like here, that would cause poor model fit as well, right? So when you specify a model, you have to be aware not only about the errors that you're putting in the model, you have to be aware of the errors you are not putting in the model, because which are the assumptions you are making, right? In this case, I'm making the assumption that age is unrelated to the part of vigor that is not explained by BSC, okay? So let's save that. And okay, got estimates, chi-square, 1.73, minimum was achieved, so the model converged, we got results. But let's look at model fit. Okay, there's a little change here. Does it have exact fit?
Oh. No.
Yes?
No.
No, because it's statistically significant, right? So statistically significant means no exact fit. The chi-square 173 has now a p-value of 0.006, which is less than our alpha level, which is 0.05, right? For the social sciences at least. And that we consider that statistically significant, therefore there is no exact fit, showing that this model does not fit as well as the saturated model, which is the model with all possible paths, right? But we are not going to stop here. Again, I told you exact fit is a very, very ambitious target.
Right. Yeah.
People don't get exact fit. We're going to look at close fit. How about close fit? Look at the IFI, TLI, CFI. Do you think we
Yes.
have? Yes, we have close fit. Root squared error 2, like 0.035, it's less than 0.05, and there's a close fit. The p-value is more than 0.05, so not statistically significant, also shows close fit. The confidence interval is all way below 0.05, also showing close fit. So we are satisfied that that is.
Can you explain that RMSCA again? Like, you're looking to get below 0.05 on one part, and you're looking to get above 0.05 on the other part.
So
You're at a 0.035, and you're saying
you
that.
want to hear this to be. This is interpreted just like.
I get that part, but the first part, the RMSE, you were looking to make.
Yeah. So RMSE, the way it's scaled is that 0 means that your model fits the data perfectly. Therefore, that's why you want to get to 0 as fast as possible.
You're using a 0.05 for that number as the barrier.
Yeah, but it has nothing to do with a p-value.
Okay.
It was just a coincidence.
Okay, that's what threw me off.
The old criteria, actually, the old criteria was 0.08. We still can use 0.08 as a less conservative, right? So this is not a p-value.
No, so we got to disregard using 0.05 for that.
Yeah, well, we were using 0.05 because Hui and Bedler found out the criteria, but it's not a p-value.
They really make things confusing, don't they?
Yeah, it's not a p-value. I mean,
They stole 0.05.
I'm okay with 0.08 here, but
0.08.
Yeah.
Okay.
It's an area that's not still a bit, even though Hui and Bedler has become the standard, as evidenced by the 290,000 citations they have, it's still a bit problematic.
Is that 0.08 and 0.05 have to do with the 0.92 and the 0.95 that we were talking about yesterday?
Yeah, it has to do with using a cutoff of 0.9 here as a more liberal criteria. Right?
Okay.
Yeah. So people are using 0.95, but which Hui and Bedler suggested, but it still may be too conservative in some cases.
Mm-hmm.
Yeah. And I showed you like the future is dynamic fit index, where you calculate the cutoff for your specific model, you know. But that there is an app for that, but it's not used very much. I make my PhD students use it, but you guys don't need to, you know, because still brand new, you know, and the researcher, Dan McNish is the researcher who developed it at Arizona State University. He's in psychology. The psychology and education talk a bit more. It will get to business research eventually, you know, but for now, people still use Hohenbettler.
But for the sake of this model, you're looking at IFI, TLI, CFI, and it's greater than 0.95. So
Yes, yes. A root mean squared error less than 0.05. Like the value of it, not most people just use the value of it, you know, like it can be, you can also use the p-value of that value, which is this, but you can't just report this. That's what actually most researchers do. Just the value of it, which is here. Oops.
And we're trying to get that below
0.05. Equal or below. Yeah, and that's not a p-value. It's just the value of the index. Okay. So now that we are satisfied with closed fit, we can look at the estimates, right? So the estimates, remember, these are unstandardized, but the unstandardized has the p-values. Now for the direct effects, we really want to pay attention to the p-values, because that will tell if these direct effects are statistically significant or not, right? And which is answering to his hypothesis, right? So the first one here is the direct effect of linear relational behavior on bonding social capital. So it's A here, right? So what Amos does, right, it provides the estimate, the standard error. The CR critical ratio is the estimate divided by the standard error, which is a z-score. And this p label is the p-value, which indicates whether it's statistically significant or not. We are using an alpha level of 0.05, right? So greater than 0.05 shows that that direct effect is not statistically significant. Less than 0.05, that direct effect is statistically significant. Statistically significant means it's not zero, right? And so now what Amos does is that if the p-value is very, very small, it only puts star, 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 meaning it's probably 0.000000 something, right? So in your paper, you would say, you know, there was a statistically significant direct effect of LRB on BSC. It'll be equals 0.24, that's the coefficient, comma, standard error, p less than 0.05. You won't be able to put the exact p because you don't know what it is. It just gave you stars here, meaning it's very, very small. So that's the APA standard. Like if a p-value is very small, you don't write it down. You just say, so you would state, just to be sure. Like, show significant, statistically significant direct effect, or you can call it direct relationship. Some, by the way, I just make you aware, in structural equation modeling, we use the terms direct effect and indirect effect. But people that do experimental studies, right, they disagree with that use because they say, oh, direct effect, it has to be an experimental study, right? And so the conservative way of saying that is a direct relationship. But, you know, so it depends on which journal you're submitting to. But in structural equation modeling, terms direct and indirect. So so direct effect or relationship with, we'll go back to what we use here. Social. We use a lot like B. This is coming from regression, right? Using beta as the general Greek letter for all these direct and indirect effects. And we put the subscript. I'll call this B1 equals 0.24. SE standard error. Always report standard errors. 0. P less than 0.5, which shows that this is significant. Now, with a model with a lot of results, a lot of times you put this on a table instead. Like this is how you would put it in a paragraph. But if you have a lot of effects, I would say put this part on the table. That's what they did, and just kind of finish the sentence over here, right? But if you put it on the paragraph, that's how you state it. You have to say what the coefficient is, what the standard error is, and the p-value. Now, if the p-value is significant but is not tiny, you can put what the exact p-value is. So, for example, for performance and vigor, the direct effect of vigor on performance, which is this one here, it is statistically significant, right? Because it's less than 0.05. But we could put the actual p-value. We could say, p equal 0.002, because it's not a tiny number, okay? And that's, do you guys, I don't know if Phil's class or any other class, do you guys work with the APA manual for, so that's the standard for APA, for p-values. Like if it's very small, less than 0.000, you put your alpha level, p less than 0.05. If it's greater than 0.000, you put the actual p-value, okay? So, do our results here support the hypothesis of the author?
Yes.
It does. Yeah.
Because the model fits and then all the
The coefficients were significant.
Yeah.
Yeah. If one of them wasn't, it would break it. Like, so if, let's say, B wasn't, then it would break this chain. And there is no way that, there would be an indirect effect of either relational behavior or job performance because this here is 0, right? But because they're always statistically significant, it means they're not 0. That's what statistical inference is, right? If something is statistically significant, you are inferring that it's not 0 in the population, okay? And that's why we would conclude that, obviously there are exceptions, assuming that you have a representative sample and so on, but it's not, most cases we don't have a representative sample. Okay.
Wait, we forgot. Remind me why some of the X1, M1 don't have any numbers to them, and why they're...
Okay, the one that doesn't have any number is the one we set to 1. Remember?
Oh, the one is set to 1, yeah.
But they do get numbers if you look at the standardized results. Look.
Oh, and that's why when you went on that other screen and you said there was 3, and we couldn't do it because you need 3, it's because we got to subtract the first one, which is the 1.
Yeah, but you still get standardized estimates. So if you want to know like what the first loading is 0.86. You know those. I didn't mean to click on it. But here we set it to 1. So we actually, by the way, I did make a slight mistake here because I shouldn't report this number here. it's okay to report, oh, this is nice. So we actually have a regression-based interpretation, which is correct, but it's not used much in structural equation modeling. This is correct. When error b goes by 1 point, BSC is expected to grow by 0.04. Now, if we look at, but the problem is we don't know because LRB is a latent variable. 1 point doesn't mean anything, right? So instead, what I should have done here is instead of reporting 0.24, I report the standardized coefficient, which is for the next table. I should report 0.443. The standard error is still the same, and the p-value is still the same, but always report the standardized coefficient because that is interpreted as standard error. So let me check if Amos gives it to you. Oh, it does. You know, it's funny, I don't remember this being clickable. But I guess it's nice. It gives you the regression-based interpretation.
Where did you click that?
I clicked on the number itself,
Okay.
and it said when RB goes up by 1 standard deviation, BRC goes up by 0.444 standard deviations, which is correct. I mean, the more precise would be when RB goes up by 1 standard deviation, BSC is expected to increase by 0.443, right? It's not deterministic, right? It's on average across, but yeah, that is the interpretation, okay? Okay, now, we controlled for age and tenure. Did you find evidence that age and tenure actually affect performance?
No.
No. Because?
P-value.
P-value, not significant. Neither one was statistically significant. Therefore, they cannot be confounders here. They are controlled for them. Do we need to, okay, question again. Do I need to, they are not statistically significant. Do I need to rerun the model removing them? What do you guys think?
Yes.
No.
No.
No,
No.
leave it.
Either.
Okay.
Just
It's really either, but I do leave it because that was your theoretical model. Now, people do, I would say where I would rerun is if you have a lot of covariates and they are collinear, right? So I would remove the non-significant ones and rerun because you may get some variation because you removed non-significant, but that's model selection, and you should avoid, model selection is complicated. There is probably tens of thousands of papers on model selection, and they show that it brings a vulnerability that the order that you remove variables sometimes matters, right? So like there is the forward process where you add a variable at a time, the backward processes where you put all variables and you take down one at a time. There is the stepwise where you add and subtracting terms, and sometimes they don't agree. And so one way of not having to deal with that potential problem is just specify a model based on theory, fit the model, and then leave there and report as it is. Like not significant is not significant. Now, but even if you have 60 covariates, then I would do model selection because it's a bit too much and may vary. You just have to be aware that having too many variables and having to do model selection of predictors may create some instability in your results. Okay?
So I have a question on that. So because we're always trying to simplify the model, right? I understand you don't have to rerun it, and it's just statistically not significant. But if you took it out and then the model still fit, wouldn't that be a better model?
Well, I mean, because okay, so you're correct in general, but not when it's a covariate necessarily, because the covariate doesn't. There is no theory building on it, right? Like you were just saying, okay, I'm controlling for this, and it turns out that they were pointless, but you know, you're really not, it has nothing to do with your theory. But yes, like in general, yes, you want to compare alternative models. But alternative model, when we talk about alternative models, we are talking about different relationships between the same variables, right? So this model here is an alternative to the author's model because it's a different relationship between the same variables. Adding covariates and taking out covariates is not an alternative model because it doesn't change the relationship between the existing variables, which is what the theory is saying, right? This is really just trying to block out potential confounders. It's important, but and the reason also, like if they were confounders and you didn't control for them, they would provide a backdoor path, which would be this backdoor path here, and therefore you get biased coefficients, right? You would still, by the way, it would not affect the model fit because, well, in this case it would, because they would become a part of the direct effect. But if you put a direct effect, then it would not affect model fit. It's just that your direct effect would be biased because it would include the relationship that goes through the backdoor path, age and tenure, right? So I guess the answer to that is it depends what your focus of theory is, right? Is this an important part of your theory or not? Maybe, typically when something is part of theory, you have hypotheses about it, right? And he didn't really have hypotheses about those, okay? And again, like when you have theory, you put in the model and then you try alternative models, which is different paths, but keeping all the variables in the model, right? Okay. So now, back to the results here. So I found these direct effects, but I'm also interested in the indirect effect. Like, so how do I get? Remember that the indirect effect is the product of A, B, and C, right? And I want to report that indirect effect, right? Because the indirect effect will be how much for a change of one standard deviation in linear relational behavior, how much the job performance change is expected to change. That's the indirect effect, right? Now, I mean, you could, but you don't have to. But it would be legitimate to just take the product here, 0.24 times 0.38 times 0.36.
Of the unstandardized.
Yeah, we could do the same thing here. But you don't have to, and there is an disadvantage because you can have Amos calculate that for you. But there is a disadvantage of just taking the product by hand is that you wouldn't get what the standard error of the product is. And the standard error of the product is not the same as the product of the standard errors. The reason is because there is some covariation between these coefficients. So computing the standard error of the product is complicated. In my PhD class, I show a whole lesson on different methods. I will just show you the best method. Okay? The best method happens to be one available in Amos, which is called bootstrap. Okay? So nobody here knows what bootstrapping is. Have you heard of bootstrapping?
We've heard of it.
Yeah, heard of it. Okay. So I'll do a quick drawing here. Yeah. So bootstrapping is really a way of resampling. So let's say here, this is your data set, right? You have case 1, 2, 3, 4, 5, 6, 7, 8. For bootstrapping, what you do is you create other data sets. Typically, we do it 1,000 times, 1,000 data sets that are samples of the original data set, but they are samples with replacement. And the advantage of doing sampling with, by replacement, I mean, when you sampled one, you put it back so it can be sampled again, so you can have the same observation repeated, right? So, and the advantage of doing that is that you can get sample data sets of the same size of the original data set. You wouldn't be able to do that if it was without replacement. So, for example, the bootstrapped data set one could be case 1, 2, 2, 3, 4, 4, 8. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, right? It means I have the same sample as the original one. Here I have 8. Here I have 8 as well. But because it was sampled with replacement, the second row was sampled twice, fourth row was sampled twice, and the eighth row was sampled twice. 6 and 7 didn't, 5, 6, and 7 didn't even make it, right? Now, obviously, I could not get 1,000 data sets of a sample size of 8, but with a sample size of 290, which is what we have here, I can get 1,000 bootstrapped data sets, right? And once you do that, you end up with, data set 1 to data set 1,000. And you run what the software does for you. The software Amos will feed the same structural equation model to each data set. So it does it 1,000 times, which shows that this method wasn't really available until computers became powerful enough to do this. Like, we'll get 1,000 data sets in a blink of an eye. It's running this model 1,000 times, and it's not even, we don't even have to get a coffee to wait for it. And what it does then, it estimates that interact effect, the product, ABC, 1,000 times. So you get ABC1 to ABC 1,000. And those 1,000 ABCs will have a distribution that will be normal, right? And the mean and median will all be the same because it's going to be a normal, and which will be, the final estimate of the indirect effect. But then the standard deviation of those 1,000 ABCs is the standard error of ABC. So, in other words, by doing this, you can get a standard error of ABC, and with the standard error, you can get a p-value, because then the Z becomes the mean here, mean ABC, divided by the standard error, and then you can look at a Z table and get a p-value for that. And you can test significance. There is even a way to calculate a confidence interval where you get, from 0.025 to, in this distribution, to 0.975, which is like the 25th, 2.5 actually, percentile to the 97.5 percentile, and that's that distance here is your 95% confidence interval. For the indirect effect. So that is the best method to get what the standard error and what the p-value is for the indirect effect. It is the best because it doesn't make as many assumptions. It's very robust to non-normality. So, and that's what we can do with Ames. Okay, it's important to do this because, or else we don't know, the size of ABC, right? Like so I want to show you that. And the other thing is, right now, for this particular example, there is no direct effect, so the total effect is equal to the indirect effect, right? There is no direct effect. But in an example where there is a direct effect, you would want to report both. So you would want to, if B here existed, or E, sorry, you would want to report both ABC and E, and you would actually want to calculate a percentage, like for the total effect, what percentage is ABC, what percentage is E, to be able to show like what percent is indirect versus what percent is direct. Okay, you see that in the Zhang and Bartol paper that you will review, that they do it's called an effect decomposition. Effect decomposition is this, when you break it down into direct and indirect. And then you, to get the percentage, right, you just do the percentage direct, percent direct is just the direct effect divided by the total, and then the percent indirect would be the indirect, which in this case is ABC, divided by the total. Now, in Carmeli's example, the percent indirect is 100%. And that we call this, when you have 100% indirect, we call this full radiation. Right? But in most cases, you wouldn't have that. You wouldn't be able to calculate the percent direct and percent indirect. Okay? So let's get the bootstrapping. Okay? I'm going to close this. I'm going to go back to the model, and I'm going to show you how to request bootstrapping. Okay? So we'll go to analysis properties. First, under output, I want this breakdown, so I'll click indirect, direct, and total effects, which means it's going to calculate the breakdown for you, percent direct, percent indirect, and total. Well, it doesn't give you the percent, but it does give you a breakdown, and then you can just calculate the percentage. Now, but these alone, it will not give you the standard errors. It will only give you the products. To get the standard errors, we click Bootstrap. We click on Perform Bootstrap. The default here is 200. Nobody uses 200. 200 is just not stable enough. What happens is, this distribution here, we want this distribution to be smooth, right? If you do 100 bootstrap samples, you probably get something like you know. And if you do 200, it gets a little smoother, and then with 1,000, it gets pretty smooth. Some cases we even go as far as 10,000. Okay, so you want this analysis to be done many times, so your distribution of ABC is pretty smooth. So we'll change this to 1,000. Percentile confidence intervals. You can request that, which would give you. You can, not every study reports confidence intervals. Every study reports the p-values, but you can, which would give this, like the 95% confidence interval calculated this way. If you want confidence intervals, you want the bias-corrected confidence intervals. Actually, we'll change this to 95. Bias-corrected means that sometimes the estimate you get from running analysis just once doesn't sit exactly at the mean and the median here. And the bias corrected adjusts for that difference between the analysis you got with a single data set that ran just once versus the mean of the 1,000 analysis. Okay. There are bootstrap versions of the estimators. We don't need that. We don't need parametric bootstrap, which is a different type with more assumptions. So this is all we need, okay? And that's all for requesting bootstrap, okay? So we can close this. Yeah, 95 is standard. We get 95% confidence intervals. So they use for elections as well. Those. I'm not great. Okay, so I'm going to save, and I'm going to rerun. So we'll get the same fitting, the same results. We didn't change the model at all, right? This output property did not change the model. We're just getting some additional things. We're getting the ABC product. We're getting the bootstrap with the confidence, with the standard errors and the confidence intervals. It's going to take a little longer. It ran 1,000 structural equation models, right? Just we didn't have to wait at all. So now the output is a little tricky to navigate because it kind of unfolds. Sometimes I get a little lost on it because like you see the bottom here is grayed out, and you have to click on the right things over here for these to become available to you. That's why sometimes I get a bit lost. We don't need to look at the model fit again because it's exactly the same model fit. We want to try to get to the indirect effects. So I'm going to click on estimates. And scalar. Regression weights. Okay. Now, okay, when I click here, it's unfolded here. It allowed me to look at the bootstrap. So the bootstrap estimates, some errors, bootstrap confidence intervals. So these will give us confidence intervals for the estimates. It's a little, I don't like how they do it in different tables, like one table for the lower bound. Well, actually it's the same thing. I don't know why they put two. So for example, for the estimate for BSC, the lower bound is 0.158, the upper bound is 0.331. This is the p-value through the bootstrap, which is not the same p-value as the original p-value. It's calculated a different way. It's calculated from the 1,000 estimates. You can report this p-value instead, but it should agree. Now, it does the same thing here. Now we have a confidence interval for standardized estimates, standardized p-value. Now let's try to get to the indirect effects. It's on the matrices. Oh yeah, it's on the matrices. Okay, so if I click, I have total effects, and it is a matrix. Like you have to match the variables. So like, for example, for LRB on BSC is 0.24. Now, what is from LRB to Vigor? Now, what you're going to get here is the product of A and B, and that is 0.993. So that is the indirect effect of LRB on Vigor. So you just multiplied A and B. Okay? So that is doing a mediation analysis for you, right, with the mediator being BSC. Now, what I want from LRB to job performance, so ABC, we would go here, the performance to LRB, okay, 0.034, right? So that is, but actually we don't want to look at, we want to look at a standardized one. So it would be the same thing. Performance, LRB, so 0.032. Cool. So the standardized, which is direct and indirect effect of RRB on performance, is 0.032. Yeah, I didn't know the clicking thing in getting the interpretation must be new, because I haven't seen it before. It's really cool. It does help, right? It's saying exactly what it is. Like, this is a total effect, so both direct. So in this case, direct and indirect, but you know the direct is not in the model, therefore it's all indirect. So one standard deviation in performance correspond to expected increase in 0.032 standard deviations in performance. I gotta say, I know Amos is old, but that's one thing you do not get with any of the other statistical software that does structural equation modeling, like clicking and getting the interpretation for you. Yes?
I was going to say, what did I leave out if I'm not getting that in my matrices tab? It's not doing.
Are you getting? Do you get a matrix tab?
I do, but it says factor score weights. Was there something I didn't?
Maybe unclick the factor score weight option when you do analysis property.
Okay.
Because that I did unselect it because we don't need that.
All right. So.
And then make sure you select total direct and indirect.
But so now do we have to back out the direct effect to
Well,
get the indirect?
No, because okay, in this case, if there was both direct and indirect, you would look at the total, we would look at the direct, we would look at the indirect. Now here we know the total is the same as indirect, so we can actually look at the indirect, which is here, standardized indirect effects. Right, and then the indirect effect of our VO performance is exactly the same as the total, as expected. But you click on it, you get the more specific interpretation. The standardized indirect mediated effect of LRB on performance is 0.032, right? So, by the way, another advantage of the standardized,
Ethics development.
yeah, it was that,
Just
yeah,
saying, click it.
yeah.
Where did you have to click?
I didn't have to unclick anything, I just didn't collect the,
Direct, indirect, and total.
yeah,
Okay.
very simple.
So note that here that it gives you the standardized coefficient is a measure of effect size, meaning it shows you the importance of the effect, right? Like 1 standard deviation change is a lot, right? Moving any variable by 1 standard deviation is hard, right? Think about how you would provide training to your executives to increase their leadership relational behavior by 1 standard deviation. And if you accomplish doing that, it will only move, on average, move the performance by 0.032 standard deviations, which shows you very clearly that that's a very small effect size, okay? Which is something that, so which highlights very clearly the difference between statistical significance and practical significance. Is that something you guys discussed like in your introduction class? Yeah. So, in theory, there is a relationship. Should I act on that relationship? Should I change something about how we train our executives or whatever you do in your company? No. Right? Yeah. So, and you have to keep in mind that for even power, like, right, we detected this relationship with a sample size of 0.29. Maybe if you have a sample size of 2,000, we would detect even smaller relationships. Like they would be statistically significant, meaning they're not zero, but they may have no practical significance whatsoever. Okay? Nice, and they cite Klein. Cool. Okay. Klein is what I use for the PhD class. It's a really good book. I do like the book. I use it in this class a lot. The problem of Klein is that it's coolant to a fault. Like it spends so much time citing the most recent research that for people that are trying to learn the basics, it's quite confusing. But like for me, that like I know the basics. I just want to see what's the latest. It's a great book, Okay. So yeah, we get the standardized indirect effects. Okay. Now the direct effects, you can see how from LRB to performance is 0. Right? We did not estimate it. It still gives you interpretation, but we didn't estimate it, so it's 0. Okay? Now, what you would put in a paper, the format here that they give is really not that helpful because it's not how you would put this on a paper. You wouldn't put this in a separate table. The way you would put in a paper is this. Actually, I will show you one of my papers. I think this paper here has a table of Okay, this one doesn't, I must have said it. If there isn't table, it's because I did it in the text. Yeah, that's what I did here, indirect relationship. See, I put it in the text. You always have to make that decision, like, is it brief enough that you can put in the text? Just kind of like I showed here. Or do you need a table? Here I put in the text. I do have one, but I think I believe I put in the table. Let's see. A bit older paper. This one here. Yeah, here. This is an example. I mean, obviously, creating tables, just like creating graphs, takes some creativity. So usually, like, we finagle with it until we think it's going to be clear enough. But I put like the outcome. The whole table is about the same outcome, and then I broke down. Direct and indirect. So for some things, they were direct and indirect. Now, these here, I did not put total, and I don't remember why, right? The total is just the sum here, And then the other thing I did not, I probably put it in the text, what percent is indirect, right? Let me see if I did it on the text. No, I didn't. I just commented like what, but it's helpful to put the percentage. It like makes it the job for the reader better, right? So here, for example, if I had percent, it would show more clearly that from this total relationship here, it's mostly direct, right? Like from 0.183, which is total, 0.145 is what? What's the percentage here? Let's see. So yeah, I could have done this a little more clear by just calculating that for my reader. So it'd be 0.145, which is the direct, divided by 0.183. Yeah, 79% is direct, right? So yeah, I could have augmented this table here by adding a percentage column for when there is so here would say, this one here, for example, would have a column. I would say, 79% is direct, 21% is indirect. Okay, and that is helpful for the reader. I mean, it's not required, but I find it helpful. Okay. Probably again, make decisions on the paper. What I could have done to make space here, you also, again, it's like Ben's and Potsakov yesterday, like you have to fit the page limit. In your dissertation, you don't have that concern of fitting the page limit. But what I could have done is instead of putting the p-value, I could just have tagged use the star system, which is acceptable, like put the stars here with this note here, to indicate the significance, so I didn't have to report the exact p-value if I use the star system. It's acceptable because someone can always calculate the exact p-value by using the estimate standard error, so it's not like you were reading anything. But that would give me an extra column to calculate to put the percentage direct, percentage indirect. Okay? Questions? So that's how you do mediation analysis in SM. Okay? Now the last thing I want to do today is moderation, which is interactions. A little more complicated than mediation. Okay?
Good.
Yeah. Yeah. By the way, you always be aware, people confuse mediation and moderation a lot. They're very, very different things. Okay? This paper did not have a hypothesis about moderation. So we're going to make it one up to test it. Okay? Okay, this is shown. Part 3, okay, we're right on that. So latent variable interactions is moderation. Like how do you allow latent variables to interact where that the effect of one variable depends on another variable. Okay. There are multiple methods. We open my slides here. The methods I teach are not the best methods because the best methods are not available in Amos. But they're good enough. Like they're not. They'll work. Right. So this is a common way to represent. This is a common way to represent moderation, where you put an arrow to the middle. I have to point out that this is a representation only. Like this has no relationship, this arrow here to the middle, there has no relationship to what we actually do in Amos to estimate it, right? What we actually do is more similar to regression, okay? Let's think about a simple regressional analysis here. Let's say you have your Y, which is a measure of performance. V0 plus V1. One variable is training plus V2 experience. Right? Residual here. Regression. And so everything here is an observed variable, no latent variables. Right? How would you add an interaction between training and experience in that model?
Multiply them together.
Yes, multiply them together. So we essentially do the same thing in structural equation model. Same thing. the variation is how we get this product, right? Because here it's quite simple because training is observed. Training is a variable in your data set. Experience is a variable in your data set. So you can just multiply them, get a third variable in your data set, that's the product, right? You would, and then you run this model. What if, well, now we have a problem that, LRB is not a variable in your data set because it's latent, right? How can you, and let's say we want an interaction here. There is such a thing as let's say there is one fancier type of interaction which is called moderated mediation, which is if the effect of one variable depends on the product of the other. Like, so let's say if you wanted moderated mediation here, let's say that let me see which one I did. Yes, just to I don't want to show a different one than the one I did. So let me just open here. Okay, yeah, I did it LRC with BSC, right? So if you want, let's say you want to say that in addition to this, there is an interaction between LRB and BSC, okay? That would be a type of moderated mediation. So the effect of LRB on job performance depends on BSC, okay? Now, these are not observed, so they're not in the data set. Look at the model I fit there. How do you think I got that LRC times BSC product if LRB and BSC are not observed? It's a hint. It's related to something we did before, which I said was like kind of an aside. Hmm? Yes, more specifically, like what did you say? Data set?
The standard error.
No, we didn't save standard errors. Factor scores. We remember we created a separate data set that we saved factor scores, right? And I said, okay, factor scores, we don't use them that much. They have measurement error. They just combining the variables, weighting the variables by the factor loadings, like combining the items. But there are some uses of that, right? And one use is to do an interaction term, right? So what I did here is I saved factor scores first when I did the CFA, right? That file we created. Then I brought that file back. I had to rename the factors. Now notice that I put an F, meaning F in front of the variable names here. Mm-hmm. I put an, and the reason I did that is because now my data set for this has the variables LRC, BSC, vigor, and performance because I saved factor scores, right? So it created, if I look at variable names, now like, yeah, it's like the same you created your data set when you saved, it has those variables there. So because they are composites, I had to call my factor something else, right? And then I created a product separately, actually used SPSS to create this product. You can't do data manipulation in Amos. Use SPSS to create this product. And then I put the product in the model. There are some extra things here, but anyway, we didn't use the extra things. Okay, that is one way. It's not the only way. It's actually not the best way. This is the worst way, as a matter of fact, because it's the simplest way. But the factor scores have error in them that it gets baked in, right? Now, when would this be appropriate? If reliability is very high. In other words, if the factor loadings of the factors that I'm combining, like if the factor loadings of linear relational behavior and the factor loadings of BSC are very high, it means that there is very little measurement error to begin with, right? Therefore, doing this product will work just fine, because even though I'm ignoring measurement error, there isn't that much measurement error. Okay? Now, that's method one. Go back to my point. Method two is a little more complex, right? So method one is product of factor scores, which I just showed to you. We can practice. A better method is called the product indicator approach. Okay? That should be the method you use because it's better. Okay? The reason it's better is because you're controlling for some more measurement error. The way you do it, okay, well, first going back, the product of factor scores, we already went over. You fit CFA, you estimate factor scores, which we did. You go to SPSS, you take the product of those factor scores, and then you go back to Amos, and you put that product in the model, which is exactly what I did here, right? So we will go back to that later. Now the next method. So this is the product factor scores. The next method is the product indicator. Now the product indicator, you create a latent variable to represent the interaction, right? But every latent variable needs indicators. And that's where product indicators come in. The indicators of that interaction latent variable are the products of the indicators of the interacting latent variables, right? So if you are hypothesizing an interaction between factor 1, say LRB, and factor 2, BSC, I can create a latent interaction factor here with indicators that are products of these indicators of those. And that's why this method is called the product indicator approach, because you are literally multiplying the items, okay? So, there are some difficulties with this method, right? The difficulties are not obvious in this particular diagram because F1 has 3 indicators, F2 has 3 indicators. But the first difficulty is, how do you figure out what to multiply here? Should I multiply
Right, that's what I was wondering.
x1 by z1 like I did, or should I multiply x1 by z2?
Yeah, it seems
right.
arbitrary.
So there have been simulation studies about that, and what the simulation studies showed is that the best approach is to order the indicators by factor loading and multiply in order of factor loading. So, the highest factor loading for F1 times the indicator with the highest factor loading for F2, right? So let's say x1 has a factor loading of 0.9, x2 0.8, x3 0.7, and in z1, let's say z1 has factor load of 0.9, z2 0.8, and z3 0.7, that would result in us multiplying them that way, because we would get the indicator of highest factor loading in one times the indicator of highest factor loading in the other one, okay? But what if, so another complication, what if they have a different number of indicators, which is the case of ours, right? LRB has 3 indicators, BSC has 4. Sometimes the difference is brutal, like sometimes one has 5, the other one has 30 indicators.
Then you have to use the less.
So again, research has, you're right, but research has done simulations about that.
Could you take an average?
They have examined it. So things that simulation studies have examined is using all possible products. You know, that is crazy. It doesn't really work unless you have, 3 and 4. Like the other option that people have examined is only using the highest for the one with the bigger scale. Use the indicator with the highest factor loading and leave the other ones out. That works. Okay, that works well. And that is the preferred method. The other option is what's called parceling. Is like combining indicators, like creating composites of the biggest scale. Like, let's say you have one scale with 5 indicators, the other scale with 30, and you would combine the indicators of the scale with 30, like 4 at a time, like creating composites. And that method, it does work if the scale has high factor loadings, but it's more trouble than it's worth, right? So simulation studies show clearly that you can do just the indicators with highest factor loading on the largest scale, okay? One of those papers is actually mine. Show you guys. It has been many years. I haven't done research in this topic in about 20 years, but at some point I did. And look at this. Comparison of methods to form product indicators for large, unequal number of items. Published this in 2011, so it has been a while in structured equation modeling. And I find that so I tried different methods here. One is create parcels which are composites of the larger scales by indicators of the small scale, multiplying the 3 most reliable indicators. Reliable means higher factor loadings of each scale matched by reliability. So you basically order by factor loading, and matching items by reliability to create as many product indicators as the number of indicators in the smaller scale. Okay. And I found that all methods considered provide unbiased parameter estimates. Therefore, because I found no difference, this was a large simulation study. And that's why I recommend the simplest one, which is matching by reliability, right? Here I actually simplified. I did like the 3 most reliable. I actually reduced both. But in reality, unless the 2 scales are very large, like in this case here, like you have 3 and 4, you can just take the 3 best here to match the 4 here. If you have 5 and 20, you can use all 5 of one, get the 5 best indicators for the scale that has 20. But let's say if you have 20 and 20, right? My results here are showing that you only need to take three. You take the three most reliable, so highest factor loadings for one upscale, and the three most reliable for the other scale. So you don't need to, even if they have 20, you can just take the best ones, and that works pretty well.
3 is that sweet spot.
Mm-hmm. 3, it allows the model to be identified, like you can fit that part without any constraints, because the degrees of freedom, you have enough degrees of freedom. I mean, it's 0 on that part, but you are not interested in model fit anyway, right? So that's why 3 is a good number, is because you have enough degrees of freedom with 3.
Okay.
Okay. So now I did compare with this is the best method, LMS, which is not available, but in this case here, it performs similarly. Okay, so that's what we're going to practice. It's going to require us to go to SPSS, actually, to do this, okay? Because, so what we want to do, I don't think, let's focus on the product indicator. We can try this too, but let's focus on the one that I recommend first. So let me open here. I'll show you what we are trying to accomplish, right? We are trying to accomplish this. Notice that I matched them by factor loading here, right? This is what we're trying to, but we cannot do this right away because we don't have these products, right? So what we need to do here, I actually may need to go to apps myself here, because I don't know if my SPSS is still valid. I don't think it is. Okay, so I'm going to have to go to apps as well. Because what I want is to open that file, and I will create these products, right? So for reference, right, we should take, before I run this, let me open our previous results. CFA Carmelli. Okay, and let's zoom in here. Oh, it's a bit of a mess. Actually, let's look at this at a table version, because these. Oh, do I have a table open? I do. We need to write down what factor loadings we want to what indicators we want to multiply, right? So if we are doing an interaction between BSC, right? So if you want an interaction here between LRB and BSC, and we want 3 indicators here. Right. We need to look at the results of the CFA to see which ones we want to match. So based on these results, we want the biggest one here is X2 times
M3.
M3. And then what else? The second one is X3 times
M2.
M2, yeah.
And then it's X1 and M4.
Yeah. So these are the products we want to create. Okay. So we will have to go to SPSS for this. I'm going to go to my browser. Okay. What is this business? Oh,
It does that sometimes. Maybe Amos?
yeah, no, I don't want Amos, I want SPSS itself. So, here. No, this is Amos.
It's under IBM's.
Yeah, it's IBM. It's under IBM. Yeah. Oh, here. I didn't recognize the icon. IBM SPSS statistics. Okay. One thing to be said about like pointing click interfaces is that you don't really forget how to use them. I don't use SPSS. I mean, just this class. And, every time I just look at the menus and figure out where to point and click. It's very intuitive, as compared to like when you write code, you have to always look again. Okay. Oh yeah, I need to do the upload data setting. Guess I'll close this for now. Here. By the way, the woman that came here yesterday for tech support, she did email me later some links about Google Maps. Should be helpful for the future. Like I'll put them in the class
Professor,
speech.
for the one like we bought the SPSS last year for this year, so do we need to buy SPSS as well?
Well, depends, right? Are you planning to do? I mean, are you planning to use it for your dissertation? Yes, then I would say so. Yeah.
For this class?
No, for this class, that's all we're doing. Like we are using it just for this limited exercise, and you need it for Zenga Bartol. So you can use UF apps, just like I'm using, right? I don't have SPSS myself because I need it just for limiting. Now, for dissertation, you may want to use it, you may want to buy it to have it handier, right? Faster and, dissertation is a big deal. I would say, it's worth the money to have get 1-year license. UF may have a discount for students, by the way. Well, SPSS does have the version for students. That would get you more flexibility in doing the analysis for your dissertation, right? Because you wouldn't have to be using UF apps. I mean, UF apps works. It's just a little slower than if you have it on your computer. Okay. So let's see. Yeah, I used to teach my PhD students using M+, and everybody was using UF apps. It worked. Now we switched to R. R is free, so everybody just downloads R. But my point is UF apps does work. It's just a little slower. My understanding is that you guys do have some experience with SPSS, right? You used it.
Mm-hmm.
Yeah, we use it.
Okay. Here's our data set.
What's the name on it?
It's what Carmeli simulated data.
Oh,
Right?
the same one.
Same one that you see at Leite. You already have it there. You don't have to.
Yeah.
Just leave. Now, so I'm gonna create these products here, right? So usually, so I'm gonna skip a step here because I don't need to, but you should be aware. Before creating these products, you should standardize the variables, like convert them to z-scores. I don't need to because those are already standardized. Okay. Now you can standardize in SPSS under analyze, descriptive statistics. I think under descriptives, there is an option here that says,
Or is it just the checkbox? Go back one more. Just cancel that
oh
little
yeah,
checkbox.
yeah, this check. Well, that's what I was looking for. Yes. So these will, if I do this and click standardized values as variables, I would get standardized z-scores for x1, right? I don't need to do it here in this example because these are already standardized, right? But you should do that if you have raw data before you do the products. Okay. Okay, so I want transform, compute variable, and I call them here x2 and 3, and it's going to be x2 times and 3, and okay, so I have the first one here, transform, compute, second one, extreme 2.
Catching up, how did you get to compute variable? Was it in data? I forget.
I did
Transform.
compute.
Okay.
Okay. Next. 3 and 2. Second one. Okay, x1 and 4. So we have our 2 products there, okay? And I'm just gonna save as I will put with product indicators. Now, if you are doing these with if you're also using Amos on web apps, you don't need to download the file. In my case here, right, because I'm using Amos on my computer, but SPSS on web apps, I would have to download this file. So I would have to close this, exit, yes. And I have to click here on the file transfer, download. Oh, just Control C. Okay, download is easier. I'm not going to download it because I do have it in my computer from before, but seems like, actually, let me try it just for practice. Yes, exactly. Slow ones.
It's 2 and 3, it's 3 and 2, x 1 and 4, x 3 and 2.
Read this again. Okay. Assuming I can get to the window where the file is. That's a funny. I'm getting to a little difficulty here because they say, you can just go Control C, but you have to get to the file first. And apparently there is no file explorer here. I'm missing something. File. Open. Okay. Or maybe here documents. Okay. Okay, that will work. That's what I was looking for. Documents. Here. Okay. Control C. Yeah, that did not work for me. I will proceed with using the file on my computer, but I will get the help people to come and tell me why I could not download this. So the computer that because either you have a CSS in your computer, you have SPS, you have both on WebApps. Okay. Okay. So going back to labels, I'm going to pick up the. I'm going to pick the structural equation model file. This one. Okay. So I just want to add the interaction, right? But I now need to change the file to refer to that one with the products, right? So I just go file, file name. So I have one here that I saved the product indicators. Now if I do view data, you can see the product indicators over here that were created, that I created in SPSS. So I can do OK. Now, hold on, just want to double check that here, it's here. Okay, so I do another factor right here. I'll use this empty space here for that. Okay, that looks beautiful. And I will I'll call this and I'll call this LRB X BSC. So it's kind of obvious that it's a interaction, right? And then I have to name these. So plugins, name and observed variables. Just add some names.
Is there a way to collectively move the whole thing up? Mine's just a little bit low.
Oh, the whole thing, yes. Like if you stay select all,
Yeah.
and then click on the little truck.
Alright, that's what I thought I was doing, and then I clicked on the arrow and it just moved there. I have to click on the box. If you click on the arrow, it moves the arrow.
Ah, okay, okay.
Thank you.
So deselect. Okay. So remember that now this interaction is exogenous variable, right, independent. So therefore, it needs to be allowed to correlate with the other exogenous variables, or else you get full model fit, right? So what I will do here is use the double headed arrow and add those correlations. Okay. So, and then for the actual interaction effect, I need to put an arrow from here to here. I'm going to try to embellish this a little here. Hold on. It's not looking like it, but I'm hoping that the touch up will help. No, I need to do more than that. Okay. Yeah, definitely improvement. So I just want to have a clear path. I want to have a clear path for my direct effect. It doesn't matter, but just will look a little prettier. Okay. So this is the interaction effect right here. Okay. That's it. Note that because I use this icon, the 1 is already here, like one factor load is set to 1. This is all good. I added the correlations. I can touch up a little more. Yeah, this is good, as good as it gets here. You guys with me? Yeah? Okay. Now let's save this. I'll do a save as. SM primarily step 2 indicator product again. That's it. I'll replace. Okay, then we can just leave everything as we did before, which is getting the bootstrap and everything as we did. Calculate estimates. Okay. Now, I can pretty much tell this is not going to be statistically significant when you look at the number. But we have to look at the detailed results. So there is no, always look at fit first. There's no exact fit. Then we look at close fit. There is close fit. Close fit is good. Then you proceed to estimates. Let's look at direct on the interaction. So under estimates and scalars, standard regression weights, we are interested in this one here. Oops. That's the interaction effect, right? What do we conclude here? Based on the line that I highlighted.
It's not significant.
It's not significant, therefore there is no interaction, right? That is, so the effect, the indirect effect of linear relational behavior on job performance does not depend on bonding social capital, okay? Let's see what it says. I'm actually curious what it says when I click on this. Okay, it just treats it as any other predictor, right? Like when the interaction goes by one performance. Okay, how do you interpret this if it was statistically significant? Let me show you. Okay, because this here in this case is not that helpful because it's an interaction. What happens is you have to think about this as an additive effect, right? Because let's say it was statistically significant, right? The best way to interpret this is calculating something called simple slopes, okay? So I'll represent here as a regression model here. Let me give you an idea. So performance, right? And we have LRB or I am not going to put BSC here because if I put BSC like right BSC controlling for BSC, there is no effect. B1 is 0, right? Because there is full mediation, right? So this model here, B1 would be in this model B1 would be total effect because I'm controlling for BSC, so I'm blocking this. Therefore, all it's left is a direct effect. Direct effect is 0. Now, if I don't put BSC here, then B1 is the total effect, which in this case, the total effect is the indirect effect. So B1 here is actually ABC, the indirect effect, right? Because total equals indirect in this particular case. You know. But then I add the interaction, which is B2 LRB times BSC. And let's say was statistically significant, right? Because if you want to make sense to do this, this is statistically significant. The simple slope is this. The simple slope of LRB is, I'm going to just reorganize the terms. I will take this out, so I'll do B1 plus B2 BSC times LRB. So I just reorganize the terms. So this is what's called a simple slope. It's called a simple slope because it shows how much y here much y changes is expected to change for each change in our B, right? But it's conditional on values of BSC, right? So what you do to try to show your readers how this interaction is working, right, is you create a little plot. You get three values, go to SPSS and find out what the 25th percentile, 50th percentile. You can actually do minimum and maximum too if you want. So, but and 75th percentile. Or you can, if you want more, you can do by this side, like 10th, 20th, 30th, 40th, 50th percentile. 3 here is just a simple graph, you know. So let's say that for BSC, if this value is like, let's say 0.4, this value here is 0.7, and this value here is like 0.9, right? It's from the data, like you find what the percentiles are from BSC, right? Then you use Excel or your favorite graphing tool to do a little plot when you put in here what these coefficients are. So B1 is you know that's the total indirect, right? You would have to go here and find what the indirect is. So indirect effects or total effects, doesn't matter. But so performance on LRB is 0.025. So this is 0.035. Now we want to know that what this is, which we can get straight from here. It was 0.014. Again, I'm treating it as it was statistically significant. It's not, I don't, you know, but if it was, what we would do, right? And then you would just do these products here to do a little graph, right? So you would say, you put RD over here. You can do this easily in Excel, like put the values of IRB. You can put all the values of IRB, or you can do, you know, percentiles of IRB if you wanted to, if you want the graph with fewer values. And then here would be performance. And you would just plug in these three values of BSC. The chair is blocking. You'd plug in these three values of BSC, right? Which would give you three curves, right? Like these are all positive. Like you would end up with something like this, right? Which you would label, 25th percentile BSC, 50th percentile BSC, and then 75th percentile BSC. And you could comment on like what the trajectory is different. I mean, this is a line graph. You can make it a bar graph if you want by taking three values of this, right? So you would end up with 9 combinations and do it bar graph instead, where you would put the bar for performance. Okay? So that's how you would interpret an interaction in regression and in structural equation modeling. It's the same idea. It's like the only real way to do this is to graphics, because the the interpretation, numeric interpretation is like, oh, okay, you know, it's 0.014 times the product, right? That's quite abstract, right? To think about, oh, you're multiplying by the product. But if you do a little plot, putting, you know, candidate values that interest you, you know, then you see how the relationship between RRB and performance is changing depending on those specific values of BSC, right? Okay? Now, if you run into that situation, it may be, I can help you do a little plot, but it's straightforward. I do this in Excel, okay? You just get some values and put that in there, and then put it on the paper and talk about it. Okay? We are out of time. Sorry, I actually ran out. Okay.